Wireless communication signals are continuous time. To convert into discrete time through the help of an analog to digital converter, we take samples ts seconds apart. This ts is called the sample interval and its inverse is fs, the sample rate. Let's see what happens to a continuous time sinusoid after sampling. When we take the samples, we replace t with nts, which makes it f over fs. So there are two things to note here. One is the scaling by fs. The other is that if and there was another frequency f plus kfs, then fs would have cancelled out and it would just be an integer multiple of 2 pi, which means the same phase. What this means in time domain is that this is a slowly varying sinusoid. We are collecting samples. This is a fast varying sinusoid and we are taking samples at the same places. So you can see after digitization they both appear to be the same. This is why we call the aliases are produced at a distance of fs after sampling. So all integer multiples of fs, we have the aliases. This is the signal spectrum and these are the aliases. So we can see that the unique range after sampling is minus 0.5 fs to 0.5 fs. To prevent distortion in the sample signal, clearly the bandwidth b which comes here and the bandwidth b which comes from this side here, they should remain apart, which means that fs is greater than 2b. This is known as sampling theorem. Not obeying sampling theorem means spectral overlap and subsequent distortion. When a discrete time sinusoid resides in our computer memory, how do we know the frequency that it corresponds to in the real world? For that we must know the sampling rate fs. For example, here we have 10 samples that define a complete period. So if the sample rate was 10 Hz, then we have 10 samples per period into 0.1 seconds per sample and we have 1 second's worth of data. On the other hand, for somebody told us that the sample rate was 500 Hz, then we have 10 samples per period multiplied by 0.002 seconds per sample and 0.002 seconds. The concept is that discrete time sinusoids are inherently tied to the sample rate. So we know that only discrete time signals can be stored in a computer memory. Similarly, only discrete values of frequency can be stored in the computer memory. Suppose that we collect n sample of a signal at a rate of fs. We can say that this is nts seconds. Now, what is the minimum frequency of the sinusoid in those nts seconds? Is it the one which completes one full cycle? So its frequency will then be given by 1 over nts hertz. Let's see what happens when we go from continuous time to discrete time. T is replaced by nts and which cancels out and we have 2 pi 1 over n. Clearly we see it as 1 over n, then we can have a frequency with 2 over n, 3 over n and so on. So we have n samples which represent our discrete frequency axis. We say that each complex sinusoid is completing k cycles per nts second. So for example, this is -9 because of the clockwise rotation and 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the complex sinusoid with 0 frequency, 0 times 1 over n. Orthogonality implies that these sinusoids, their correlation at time shift 0 is 0. Let us see, this is the mathematical formula, but this is very easy to see through the diagram. So you see that this is a sinusoid given by 2 over n and this is the frequency given by 1 over n frequency. So when we have a complete period of it here, this one is negative. When we have a complete period here, this one is positive. Definitely those two values, when we add them up, cancel out. So in complex domain, we use this formula. If it feels cumbersome to you, just see that this is a frequency is different than this one, so their correlation is 0. They are the same, their correlation is n, their correlation with this is 0. Similarly, the correlation is 0. So basically it has complete correlation with just one frequency, and this is what orthogonality is. So that the unique range we said was minus 0.5 fs to 0.5 fs, which we can also be written as f over fs from minus 0.5 to 0.5. So we chop it down into n parts. By n parts, we say we name the last point minus n by 2, and to the other end we have n by 2 minus 1. And then we take k over n becomes minus 0.5 to 0.5 minus 1 over n. This gives us the second fundamental relation for DSP applications, which is f over fs equals k over n. K over n is equal to f over fs is the formula to go from the continuous frequency to discrete frequency. Always remember this one and it will help you a lot. The concept is simple, as we said. From minus 0.5 fs to 0.5 fs, chop it down into n distinct points, and that is what our frequency axis is. For example, somebody told us that I have a frequency axis with all these n samples and I want to know the frequency which represents the sample number 2. So we say, okay, there are n is equal to 32 in our example and f is equal to 3 kilohertz. So that means that the actual real world frequency is given by k over n into fs. 2 over 32 into 3000, which is 187.5.
There are a few interesting concepts we will learn in this flow graph, which is related to sampling theorem and the effects of aliasing. As opposed to our previous approach, now we see we have started with the complex signals, which is visible from these blue data types. As we saw earlier, the blue data types are complex float 32. These complex signals imply that there is a both I and Q parts of the waveform. So let's start with our approach of doing these things block by block. So the ID, the title, sampling and aliasing, because it will discuss sampling rate and effects of aliasing. The output option is Qt GUI. Now waveform chooser is a different block which we are using it for the first times. We have three options. The maximum we can have is 5. 102 option means a cosine waveform, 103 is a square waveform, and 104 is triangle. I've chosen radio buttons in a vertical setting. Qt GUI hint basically tells us that we can leave the space blank, but then it's on the discretion of the program to display the windows on different places. But once we choose this it's a matrix kind of option. So 0, 0 is the position, 2 number of rows, 1 is the number of column. This is the sample rate. There are a few things interesting here. One is that the GUI hint is 0 and 1. So in the first row and the second column, and it only spans one row and one column. Now we again have a chooser, and we have, instead of the previous approaches where we had a fixed sample rate with a name variable, we have three different options: 8000 hertz, 16,000 hertz, and 32,000 hertz. We will see why we need these. And like before, we have a signal frequency slider which goes from minus 10,000 to 10,000 hertz, which steps up 1000. With these things in place, the signal source is just a waveform. Now this waveform is the ID of the GUI chooser. We remember we just define them here. Signal freak is the variable here defined in the Qt GUI range. Amplitude 1 and no offset, no initial phase. Throttle block we have already explained is to limit the CPU resources used by this flow graph when it runs. And the time and frequency waveforms, I always recommend choosing the number of points according to what we want to do. Never go to default Qt GUI time sync number of points options. With these settings in place, let us run the program. So here we have the option to choose the waveform, the option to choose the sample rate, the signal frequency, the slider, time domain waveform, and the spectrum. All these GUI hints you can go and check in the blocks here. We have a cosine waveform with a frequency of 0. So 1 is the I part, 0 is the Q part. Let us change the frequency to 1000 Hertz. We can see a complex waveform. It's a complex sinusoid which has, just to avoid confusion, for example, if someone is watching the video where you cannot really discern between these two and it's then we can go here and we can name them legend yes I and q, so that just becomes a little easier to understand what's going on if someone is new to complex signals. So a complex signal again is not an intimidating concept. It is just a combination of two real signals which have a phase difference of 90 degrees. So in phase and quadrature. Since frequency is zero, we can see the spectrum is zero. With 1000 hertz, we in the time domain waveform, we can easily stop it and measure. We can see the one period will be doing in 1 millisecond. And here we can see that this is 1 kilohertz, the spectrum. The sample rate we have chosen is 8 kilohertz. What happens when we increase the sample rate? Sorry, when we increase the signal frequency, 2000 hertz, 2 kilohertz. Can we go on indefinitely? You can already see that this is not possible, and there is a relationship between the signal frequency that can be represented by the discrete time samples and the sample rate. And the interesting thing starts here when we do the signal frequency as 4 kilohertz. You have seen that something has come back over here. So 4 kilohertz, the period will be 0.25 millisecond, and the signal energy is now appearing at both 4 and minus 4 kilohertz. So this is what our sampling theorem says, as discussed both in the lectures and the text. So for a signal frequency, the sample rate must be at least twice the highest frequency appearing in the signal. So in our case, 4000 hertz, 8 kilohertz. Now, if we go to 5, then 5 twos are 10. That means the 8 kilohertz sample rate becomes insufficient. And this is, we can see this is the case. It has not gone to 5 kilohertz, it is gone back to minus 3 kilohertz. Why is that? Because of the periodicity of the spectrum after the sampling operation. If we had a wider representation from minus infinity to infinity, then we would have seen an infinite number of copies all spaced fs apart. One would still have been on 5 kilohertz, but 5 minus 8 is minus 3. So minus 3. And then other would have been 5 plus 8, 13. So that would have been on 13 kilohertz. The next copy, as you can already imagine, is minus 3 minus 8 minus 11 kilohertz. But obviously we can only see anything between minus fs by 2 to fs by 2, and this is why the copy at minus 3 kilohertz is visible to us. Similarly, if we go to 6 kilohertz, it becomes 6 minus 8 minus 2. How about if we increase the sample rate? 6 kilohertz times 2 is 12 kilohertz. 16 is an option which is greater than twice that frequency, and that's why we easily see that 6 kilohertz is being represented. 7 kilohertz, same thing happens with fs by 2. In this case, fs by 2 is 8 kilohertz. So signal energy appears here and here. And anything beyond that, 9 kilohertz comes back to 9 minus 16 minus 7. Is it at minus 7? Yes, it is. The next copy would be, the actual copy would still be at 9 kilohertz, but the next one would have been 9 plus 16, 25 kilohertz. How about 10 kilohertz? We see 10 minus 16 minus 6. Now 10 twos are 20 kilohertz, which is less than 32 kilohertz, which this implies that if we choose 32 kilohertz as our sampling frequency, sample rate, then the signal frequency would be the actual one. You can see that this is 10 kilohertz, and then now we can do anything we want, and we can represent all the frequencies between minus fs by 2 to fs by 2 without undergoing any aliasing. Aliasing implies that spectrum from the neighboring zones traces back into our primary minus fs by 2 fs by 2 spectrum. This is aliasing. The same concepts can be repeated with a square wave and a triangular wave. But right now, my purpose is not to show you what the aliasing in terms of those signals, I will want to show you what their waveforms, what their spectra look like. So let's choose a sample rate of 16 kilohertz and a square wave. If a frequency is 0, obviously nothing happens. With a frequency of 1 kilohertz, we can see something interesting happening, and which we will discuss later. Remember that the discrete frequency is f over fs is equal to k over n. If I had chosen my own FFT program to plot these, then would have clearly seen the frequency bins. To quickly show the effect with real signals, let us change the waveform from complex to float. If we run the same program, we have already covered that the spectrum of a real sinusoid is displayed by two different spectral impulses. So 1 kilohertz, 1 kilohertz, minus 1 kilohertz. Their amplitude is half as compared to what would have been for a complex sinusoid. 2 kilohertz, 3 kilohertz, 4 kilohertz. They join together. Now, what happens at 5 kilohertz? 8 minus 5 is 3, and minus 8 plus 3 is minus 3. This is what aliasing is. The actual spectral impulses are at 5 kilohertz and minus 5 kilohertz. The spectral impulses we are seeing here, this one is coming from the copy at plus 8 kilohertz, minus 5 kilohertz, which is 3 kilohertz, and minus 8 kilohertz plus 5 kilohertz, which is minus 3 kilohertz. So this is what aliasing is in the context of real signals. And then we have a square waveform, and you will see the symmetry, which was not there in the complex signals, and the triangle waveform.